Today, we will be talking about audio and video analysis. The main topics that we'll be talking about today, improvements in speech recognition, audio analysis, updates on video, image analysis, updates on video, a new function used to visualize results of analysis called highlight video, updates in object detection on images. In version 14.1, the backend for speech recognition was switched to Whisper. Initially, we were using a pretty old neural net called Deep Speech 2 that was getting more and more outdated. With this new backend, we gain a lot of things. We gain speed, we gain quality, we gain language support. It has been an overall gigantic improvement. You can see speech recognize works exactly as you have been used to. You pass it on the object and it spits out some result. So first of all, what is Whisper? Whisper is a neural network that was developed by OpenAI. It is based on transformer blocks, which is the technology that powers most LLMs, large language models. And this is kind of an application of that technology to audio signals, which was, I think, one of the first, was this successful. So what happens when you pass this network on the object? Well, first, it is split into 30-second segments. It is encoded as a Mel spectrogram, which gives information about amplitude and frequency content of the signal. And it is encoded into a tensor using transformer and encoder blocks that use self-attention. You can see this is the encoding part of the network in this diagram from the Whisper paper by OpenAI. So we go from an input audio to a tensor that represents something that is semantically relevant to the words spoken in that recording. Now we need to decode this, and this is performed using transformer decoder blocks that use cross-attention, so they can pay attention to the previous tokens and the encoded data at the same time. And talking about tokens, which is what the model outputs, there are special tokens that can be included at the beginning of the transcription to steer the decoding. In this case here, you can see kind of a diagram that shows different types of special tokens in yellow that tell the model what to do for the next decoding steps. You can tell the model what language the input is in, or you can tell the model to automatically decode the language. You can tell the model to transcribe or translate. And you can also tell the model to include timestamps corresponding to where specific segments of the audio were spoken. Once you get your sequence of tokens, you decode those and into a string, and you can then just end up at the usual results that you expect for speech recognize. There are massive improvements in quality with this version of speech recognize compared to previously. Here I have a clip of Martin Luther King speech, and I can show you the comparison of the output of the new speech recognize, which looks excellent in my opinion. I just did an excerpt of the old speech recognition that we used to have previously, because it is also very slow. And you can see there are mistakes, there is no capitalization, there is no punctuation. So the quality improvement is, in my opinion, pretty gigantic. As I said, now we have punctuation and capitalization. You can see here a comparison of the old result with the new result. We get a massive improvement in speed as well. On an Apple Silicon machine, the speech recognition moves at 65%. The speed of the, is 65 times faster than real time. So about a second per minute of audio, while the old method was doing about 30 seconds to decode 1 minute of audio. So massive speed improvement. And it supports transcription in a pretty extensive variety of languages. The quality varies language by language. So the basic uses are pretty intuitive. The main one, give it an audio recording, it will return a string. The second argument tells a speech recognizer how to subdivide a transcription, either by sentence or word, other kinds of type of segmentation. And then you can return different properties. And one interesting new property are the time-based properties. In this case, this one is called interval. And you can see it tells me that this bit of sentence happened between 0 and 5 seconds. Now, these intervals are generated by the neural net, so there is no guarantee of them being accurate. And you can automatically translate an audio signal from an arbitrary language to English. So I'll record something in Italian. Buongiorno, come va? Yeah, so we can only translate to English. This is a limitation of the neural network itself, but this could be an interesting improvement in some workflows. Another side effect that we get from using Whisper as a backend is that we know we can detect which language is being spoken in a recording. We can do this through classify of spoken language or language identify, both. This has been integrated into video transcribe, which is a new function that automatically performs speech recognition and injects the result of that into a subtitle track. So here we have a video that contains just an image and then the audio track of the speech that we listened at before. Using video transcribe, we can inject a subtitle track.
On this promissory note, insofar as
there are subtitles now in that video. Another addition has been adding styling of subtitles. So in this case, I am changing
63 is not an
the color
but
of
a beginning.
Subtitles, but this accepts a lot of style specifications. Talking still about audio analysis, a lot of audio analysis functions have native support for video. Before you had to extract the audio track and then apply the audio function onto the resulting audio object. In this case, we just apply these functions to the video itself, and you can see the spectrogram, the audio plot, and in this case, the loudness of the first audio track of that video object. Speech Recognize has been improved and has support for video directly as well. Similarly, we wanted to have image functions also support video. In this case, if you do color negate to a video, it just applies that function in the video itself. In the new version, we are adding support for a lot of image analysis functions as well. So by that, I mean functions that take an image as an input and have an arbitrary return type that is not an image. One example of such function is find faces. And in this case, the output is then packaged as a time series. So you can look at it whatever time, and you'll see the bounding boxes in this case for the faces present. One new function that we added to streamline workflows stemming from this is highlight video. So we want to take a video as an input and give a highlighting specification very similarly to highlight image. The difference here is that this highlighting specification doesn't need to be static and applied to the whole video. It can be dynamic and changing with the advancement of time or frame to frame. So in this case, I am using time series that was produced in the previous slides by running find faces on this video and just highlighting that. And you can see how that highlighting works seamlessly without any need for extracting data. Another thing that was improved in this version was a new backend for image cases. All of its related family of functions that perform object detection on images. And the output should look exactly the same, but the quality of the output should be superior. For example, if we compare the legacy method with the new method, you can see the new method, on average, has more positive detections. It can now run on GPU on Mac using the ONNX evaluator. And you can see that the timing is dramatically faster. So this is a big quality of life improvement. And all of these also support video as well. So if I pass the video, it will output a time series like all the previously mentioned analysis functions. And these, for example, this is image bounding boxes. And at each step of the time series, we'll get associations with the results of the bounding boxes. And that result can be passed to highlight video so that items can be highlighted in a video in a time-dependent manner.